Okay, so today we're going to talk about parallel Python, and basically we're going to see if we can use all those cores that we all have in our machines now. Even our laptops have at least 2 cores, and even if they have 2, they like to pretend they have 4. What are we going to do with that, and how we're going to use that? And this becomes even more of an issue when we go to our cluster, when we're doing HPC, where every node right now at the GPC has at least 8 cores. And this is only going to get worse. Newer generations, you'll find nodes with, 24 cores. So you'll want to know how to use them. At some point, you'll also want to know how to use not just the cores in one node, but in multiple cores when your program grows or your problem grows so big that you'll need them all. So we'll look at that at the end too, how to do that. Now, doing this with Python is a little bit strange. The idea behind Python is to be a high-level interpretive language. And both of these aspects, high-level and interpretive, are at odds with high performance. Interpretive means I give it a command, it reads my string, it parses it, it figures out what I want to do, and then starts doing it. And it does that with every string, one at a time. That is slower than doing something in a compiled language where you give it a whole source code and all the lines are looked at once, and then some binary output, some executable is created with all kinds of tricks. All those tricks aren't possible when you're doing line-by-line interpretation. And the high level means that a lot of things are done for you. So for instance, arrays in Python know how long they are. Arrays in C do not. And so there's things that the language keeps track of for you in its types, in the way it does things, that make it easier to write things in, but means that a lot of things are done under the hood. If you could, and some of these things might not have to be done every time, but Python doesn't know which ones have and do not have to be checked. So, but no, it is a nice language because you can be substantially faster in developing things. You can fairly quickly write a prototype of a computation. Okay, so knowing that, knowing that for real high performance, we might at some point have to go away from Python. I nonetheless want to show you a few ways to get performance out of Python where at least you're using those multiple cores in your machine. So I said it already, but the thing that makes Python not so fast is this translation by line, and so it can't. Python can't optimize. It doesn't know what your next line is going to be. Now, you could say that's not really true. I usually give it a script, so why doesn't it? But that's because Python has to be able to work in both modes. And so while it's conceptually possible, it just doesn't do this. It's dynamic, which means I can have a variable x that is an integer at one point and an array of doubles in the next line. And so it has to keep track of what the type is of each of these variables, rather than them being fixed. And that means there's extra overhead of all that checking. It does memory management for you. You declare an array, you copy the array. Once you don't use it anymore, and actually once you can't use it anymore, Python will clean it up for you. That's great, but that means that at some odd point in your program, suddenly Python might decide to start cleaning up and become a little bit slower, just because of the stuff that has to do behind the scenes. Okay, so all of it interferes a little bit with high performance stuff. But we can write nicer, cleaner and more concise code. It's very flexible. We have lots of packages at our disposal. We'll see a few of them come by. And that means that we can really be very productive in writing new functionalities. Okay, so that is the great thing about it. Where you get your worst performance hit is when you're doing computations that are what I would call tightly coupled, where you don't have a lot of data. You have a lot of data and fairly little operations per data point. So think about summing values in a large array. For every point, I have one operations to do, just adding. So the fact that for each element, I have to get this element, check what its data type is, do the operation that is allowed for that data type, check if that is allowed for that data type. All those checkings per element are way more than the summation that I really want to do. So in that case, Python is not really good. Okay? But if I have a set of data, and on each data point I have a lot of work to do, then it doesn't really matter that much whether I do it in Python or C. So if it's tightly coupled, you'll get your worst hit. If it's loosely coupled, so not as much computation and not as much interaction between the points, then Python isn't so bad, although it's still slower. Okay. If you're doing a lot of file I/O, a lot of these differences start to go away. If you're just reading in a file, that's pretty much as fast from C as from Python, as long as you just make sure you read it in big chunks. So if you're just doing post-processing of a file, probably doesn't matter so much. Okay. Now, to get around these things, people have come up with a couple of packages. The most common thing that people will recommend to you is to use NumPy. NumPy is a way to go away from lists to arrays, and the big difference really is that an array is a list in which every element is of the same type, which means that essentially it only has to check an element's type and the allowed operations to it once per array. So that gives you a speed up. So we're going to see a few ways of using some tools to get better performance. But the first thing is to know where to improve our code. So if we have a script that is running okay, but a little too slow for our taste, and we want to know if we can just throw some extra cores at it and get it to be faster. What we need to know is where to do, because if the script is, I don't know, 1,000 lines long, or maybe it calls other scripts, etc., where do we start? And so before I show you how to make things faster, I want to show where it is slow. And so that's why I'm going to show you a few what I would call performance tuning tools, already performance inspection tools, specifically for Python. They exist for almost any language that cares about performance. They exist for Python too, but you kind of have to know what they are. So when I say that I want to tune the performance, or I want to get maximum performance, there's actually different dimensions in which I can maximize my performance. Usually we just think of time. I want this to get done as fast as possible. I have my script, it has to be faster than the minute I have to wait. I want to wait just 1 or 2 seconds. That's one metric. But you might also be constrained in memory. Maybe your file that you want to read in, is 80 gigabytes, and you have 16 gigabytes in your memory. It doesn't fit. You got to divide it up. So now you're maximizing your memory rather than your CPU. You might want to maximize throughput. Maybe you don't care how fast each element of each script goes, but maybe you have 1 million of these scripts to do. You don't care that each individual script is done faster. You want the whole bunch of them to be done as fast as possible. So now throughput becomes your performance metric. So all of these things are different, and usually it's a constraint. You're pushing the limits. You find you either aren't fast enough, but your memory is no issue, or your memory is not big enough, and the speed doesn't matter so much. But you're going to hit the limit of one of these resources. So the first thing we'll focus on, because it is the most common one, especially when you're just starting with toy problems, is time. So I'm going to call that temporal profiling. I don't think anybody else calls it that, but I had to have a word because I want to contrast it with memory profiling in a second. So I can do this fairly simply, just measuring the time that something takes. So here's our own old script, TTH likelihood, but it was modified by Marcelo to save its output into files rather than show them on the screen. So I've called that TTH likelihood save fix. And I can run that through Python with the data file that we had before and see just how long it takes by just putting the keyword time in front of it. This works in Linux, and it'll give you how long it took. And then, of course, I'm going to change the code, and it's going to run faster. Now, a few things have to be pointed out here already. I see 3 numbers. So if you haven't played around with the time command, this is fairly confusing. Excuse me. But if it's just time that you care about, like how long does it take, you want to look at the real time. The real time here is 19.12 seconds. But then there's 2 more numbers. One is the user time, and the other is the system time. System time is typically time that isn't spent in your script, but somehow in the operating system. And usually it's I/O, like reading files or something of that kind. And the reason that matters is that you really don't have much control about the system time. So even if we did our absolute best to make the script as fast as possible, we are probably still stuck with something of the order of 4 to 5 seconds of system time, because we will still have to read those files and write them out. Okay? Yeah. 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 So it runs it. It basically does a timestamp before and a timestamp and after, and then some counters. So it really runs it. Yeah. Which means it's accurate, but it doesn't do an estimate of how long it would take. So this tells me how long it takes. It will tell me how long my newer version will take if I try to improve things, but it doesn't tell me where to improve my version. And for that, I want a more fine-grained idea of what's going on in my code in terms of where it spends its time. And so I want to profile by function. That's the first thing I could try. So if I have a nice script that has stuff bunched up in functions, or maybe there's a module that has functions in it, I want to know how much time is spent in functions, then that's one way I can go. But maybe I've not been so diligent, or maybe my functions are fairly big. I want to know how much time is not just spent in a whole function, but in each line of each function. And so in that case, I want to do profiling by line. And the two are both possible, but are served by different packages. So for the function one, it's a standard package called SeeProfile. It comes with Python, so you don't have to install it. Whereas for the line by line one, there's a package called LineProfiler, which is fairly standard. You can just install it quite easily, but it might not be installed yet. So let's look at SeeProfile first. There's a SeeProfile and a profile. They do the same thing. I think SeeProfile is a little faster because it's written in C. So you use that. And what you do is you want to run the same Python script with the same data, but now you run it through this SeeProfile module. So this command, python-m SeeProfile, loads the module first and then runs this. And then there's an option as cumulative, which just means that I can see the cumulative time where time is spent. So what I can see here in the output, and you have to stare at it a few times to know what it says, but I have the number of calls for each function, how much time is spent in it, how much time is spent in it and in any subcalls, and how much time it's spent per call. So it lists it in order of how much time is spent here. So most time is spent in this thing called SafeFix15 module. This is because this script, I'm running the script. The module is the script, so it calls the script the module, and it's not a function. It's just plain Python code, and so it doesn't have a function name for it. In contrast with, for instance, the second line, where there's a function called likelihood in the script, and a function called Poisson in the script. In this case, this is the module. So it spends most of its time in the module, but this includes any time spent in these two. So it doesn't tell me a whole lot, except that my script is taking about 19 seconds. It does tell you the overhead of running profile, because before we were well under 19 seconds. But hopefully the relative weight of the different functions will not change. But it doesn't give me a lot of detailed information. And so this only really works if you want to know which function to look at. But if you only have two small functions and a big script, it doesn't tell you that much, right? So the next thing to try in this case is to do a line profiling. And for that, you want to use the LineProfiler package. And so this becomes a little bit more involved, because you can actually pick and choose which functions you want to keep track of. So suppose you had 100 functions, right? And you wanted to know how much time is spent in each line of each function. You could do that, but you could also say, no, I only want to look at these functions or that function. Maybe there's some functions that are just lower level functions that you use all the time. You don't want to know, you want to know the bulk of it. So to have that control, you have to do something to the code. And so rather than saying flag which functions you do not want, it works the other way. You have to flag the functions of which you want to count how much time is spent in each line. So you're going to decorate, that's what it is called, your functions with this little string called @profile. I have an example in the next slide. And then we can run the command current prof, which comes with the LineProfiler, with the script, or with the script name and any arguments. There's some arguments here. -L means that you really want to keep track of lines, otherwise it does the function thing that we already had. And -V means show me the output, which sounds funny, but it also produces output in this script. Okay, so let's look at the code first. So suppose I have a little script here that creates an array of about 4 million values of 1. And then it creates that string, or that list, I should say. Then it prints out x0 and some other stuff, and then deletes that array again, and then prints it. It doesn't do much, except it uses an array and it does something. This can't be run through either the function profiler, because it just gives me 100% of the time is in this script. There's no functions. But it also can't be run through the LineProfiler like that, because I have to say which functions I want to keep track of. And since there's no function yet, I have to wrap this thing in a function. So this is kind of what you do. And it's actually not a bad idea to have this structure in your code anyway. So this is all the same as before. I put it in a function which I called main, because I like C. And I call the function main from the script. And this is actually a way in which you would usually see this advertised as doing this. Okay. So this calls the function main, and now I want everything in the function main. I want all its lines to be counted, and the way I get that done is I put this @profile in front of it. That's all. Once I've done that, I can run this current prof command and with the name of the script. Or in our case, I could run current prof -L-V tth likelihoods _ function. So this is the same script as before, except I've put everything that was one big script into a main function, kind of like this. If you look at the code, you'll see that that's the case. Right. So if I do that, I get a whole bunch of information. So for every function that I had in there, and for every function that I put an @profile in the front of, I will get a line-by-line breakdown of how much time is spent there. So now it does it by function, which helps a little bit in keeping this clear, but that means that does mean that you have a long list of output. You probably want to put this in a file and just view it somewhere else rather than in the command line. So for this case, for instance, the Poisson function here will tell you how much time each line was hit, how much time it's spent there, how much time per hit, and the % of time within that function. So in this case, these comment lines aren't counted, as they shouldn't, right? There's no time really spent there. And the definition itself doesn't do anything else either. But it says that I hit this line 9 times. The time was about 8 million per hit. That means this divided by 9. And 100% of the time is spent in this. Now, it can't be any other way because there's only one line of code in here. But there's quite a bit of stuff going on in this line where it's computing things. Okay. The unit of time, by the way, because this is 8 million watt, is at the very top, so it's in microseconds. So that's for one function, and because it has one line, it doesn't tell me all that much. Here's the next function, likelihood ABC produced. And here we get more information, so I'll scroll down. We get per line, we get how many times it hits, what the time spent was per hit, and what percentage that means. And we see that this line here, where we're computing the Poisson distribution for this particular set, is 100%. Something funny happened here with tabs, because it should have been indented. So this one does tell us something. Like within this function, most of the time is spent in computing this Poisson call. So the Poisson call apparently is very important for our likelihood function. And then the last function that is in here is the def main, which is just everything that we had before. So I don't know if you remember this arc parse that Marcelo showed last time, but that's where it starts, and it keeps on going and going and going. Now, it's a long output, so usually you either save it to a file and then you look at it that way, or maybe you filter it on the command line because you're handy with Bash. So I could just take the output again and sort it by the 5th column, which is this percentage time, and then just look at the last 11 lines. I see these 100% lines for the Poisson and inside the Poisson, and a whole bunch of percentage of plots. Now, this doesn't sound right because we have more than 100% time, but remember, these were originally inside the functions. So, it's not quite a fair way to show it, but it does show all the lines that are important. And so all these plot lines are important, but what they all have in common is they're all just calling this likelihood function, which itself was quite important. So the reason that these show up, and we can't really see that because these are kind of one-liners, is that we're calling likelihood, which in turn is calling Poisson. So we have to deduce rather than know it, that Poisson is a very important, expensive function that is called again and again and again, and there's a lot of work for us. Okay? If we wanted to make sure that it was the Poisson thing and not the plotting itself, we would have to basically rewrite the code, make it 2 lines, one that creates the likelihood array and the next one that would plot it, and we would see which the relative time spent in the plotting versus creating the likelihood curve or likelihood array. But we don't. There's just no way. Python is line by line. There's no way it can go any deeper without us doing something to the code. Is that clear? So we're gonna attack this Poisson function, I think, because it seems to be at the heart of our computation. Now, before we do that, let's look at the other possible dimension of resource, memory. You do want to worry about memory, especially in Python calls, because when it goes wrong, it becomes very hard to figure out what is going on. And in a system like Scynet's general purpose cluster, once you run out of memory on a node, what happens is quite inelegantly, the whole node basically, as far as you are concerned, crashes. So in the best case, this means your application crashed, which means we don't have to do anything, but your job is gone. And in the worst case, something a bit more worse happens and we have to step in. But regardless, your job is gone, you don't get your output, you don't know what happened, just because you ran out of memory. And why can that happen? Well, it can happen because you might not quite be sure of how much memory you're taking, but even if you are, some Python objects might take more memory than you expect. Some Python functions might be calling or creating sort of auxiliary arrays that might be big and are taking more functions. And all of those arrays might linger for a while until Python finally decides to garbage collect them and release them, if at all. If you had one big script without functions, this is another reason to call to use functions, those arrays are never released because there's a name associated to the array, and as long as there is a name, you could use it, and Python go, well, if you can use it, I can't throw it away. Okay, so whereas in functions, once you exit a function, you can't get to that array anymore, and Python goes, well, if you can't get to the array, I might as well throw it away. So that's how the garbage collection works. But it means that if anything like that happens, you have to hope that Python does a bit. And so tracing your memory can become important if you see that your scripts just crash for no reason. For that, there's a similar utility to LineProfiler called MemoryProfiler. The good thing about it is that it needs the exact same instrumentation with @profile as the LineProfiler. So once you have your code adapted to do a line profiling, you can do a memory profiling right away. You need a PS-util module as well on Windows, but that's a detail. And you call it slightly differently, but we've seen this kind of syntax before where you say Python -m with a module name and then the script. And in this case, I won't show it for the actual script, but for this example we had before, it gives you an output where it says what the memory usage is and how much is incremented. So as soon as I created this list, you can see I got an increment of 32 megabytes, and when I delete it, it releases it again. So I can do things like deleting arrays in Python to help things a bit. Usually you don't think you have to, but if you're really strapped for memory, you might. Okay. This will be useful when you really consider big cases or you have these unexplained crashes. But for now, let's focus on the time to solution metric. So if you want, you can try this. I didn't see anything too surprising. Okay, so suppose we know where our problem is now. It was in this Poisson function. Not a problem. Our slowest part. We still don't know if it's slow for a good reason, but we know what to try, where to try things out. And let's say we want to paralyze this. What can we do? So using multiple cores, there's a variety of approaches that you can take in Python. And they all have their advantages and disadvantages. I can't explain them all, so I'll take two, which are sort of they have counterparts in other languages too. So we're going to look at Numb Expert, which is a way of parallelizing on a node using shared memory and threads, and MPI4Pi, which you can use to do a computation across nodes. Just to remind you, I think we talked about this before, processes and threads. It's annoying to have to make this distinction, but it is good to keep this straight. Think of a process as an application that's self-contained, and threads as workers within an application. These workers, threads, they can see the same memory, they can work on the same problem, whereas different applications aren't supposed to touch each other's threads. They can't. That means that different processes could live on different machines, and that would be fine. And so that's typically what you would do. You would have to have different processes on different machines. You can't have different threads on different machines, on different computers, because they can't talk to each other. They have to have a shared memory for that. Now, the reason you make the distinction and you don't do just let's call everything a process. Why do we need to have threads? Is that threads are a lot cheaper. So if you have an application that needs to use, say, 8 cores, I could use one application with 8 threads. Or I could say, well, I just run 8 applications, each of them is a process, and I'll find a way to communicate between them. And so the latter case needs all that communication overhead, and each process is a little bit more heavier than a thread. So it's more overhead. I have no choice to do that, but to do that with multiple nodes. But on one node, usually the threading model works very nicely because it's kind of light and lean. So that's why this distinction is practical for the most part. And important, but conceptually the difference isn't big. That's something to keep in mind. So this is saying the same thing. Threads are lightweight, simpler to program as well because they can count on the memory being shared, and so that simplifies a lot of programming. I don't have to explicitly copy things, and they're a little bit more portable than, say, fork processes. So let's look at Numb Expert and see how this helps us parallelize our code. So Numb Expert is two things. It will parallelize things, but it's also a just-in-time compiler. So this idea of where I said, well, Python can't give you all of the speed because it can't look into your expression and do all kinds of tricks to speed it up. Numb Expert is in essence a compiler, a just-in-time compiler for NumPy expressions. It can't do everything in Python, but it can do some very common expressions, and we'll see which ones. So it can take a vector or a matrix expression and compile it. And then as it is compiling it, it can also spread it among different cores, and it uses threads for that under the hood. You don't really see much about these threads, except that you suddenly see a speed up. Now, to do this compilation, you essentially have to give it a bunch of code to compile as a string. So rather than having your Python expression just in the code, you wrap it in quotation marks and you give it to Numb Expert to compile. So that can be a little bit awkward or awkward looking anyway, but it can really help. And as I said, it uses these threads. So what can it do? It can do basically array arithmetic. You have one array of n elements and another array of n elements. You want to add them. That's the kind of stuff it can do, element by element operations. It can do plus, minus, star, multiplication, division, power, modulus, left, right shifts, etc., etc. It also knows about a few functions. These are typically the functions that you also find in NumPy, so sine, cosine, tang, arcsine. So what happens if you give an array to this sine function in Numb Expert is it takes the sine of every element and returns the array with the signs of each element. Okay. Yeah. I think it's a not. Yes. It's not that commonly used, that's true. And then you can do some what are called reductions, where you take this array and you sum them all up to one value, or you take the product of all of them. That's called a reduction, because you take a lot of numbers and you get one reduced. So how does that work? Well, here's an example. I'm creating two arrays, A and B, with 10 million random numbers. I also initialized an array C, but in this case, I don't think the initialization is all that important with zeros. And then I'm computing A squared plus B squared plus 2AB, and I store that in C. And I'm doing this in IPython, where I have this convenient %time keyword that's kind of similar to the time statement in Bash. That gives me the time. And you see here the same kind of idea of a user time and a system time and a total time. In this case, system can also be some of the Python systems, so this is a bit more skewed. But yeah. So this is the NumPy, and this is already not that bad. If I try to do this by putting in a for loop and going truly element by element, so for I in X range 10,000 or something like that, and then do that explicitly, it'd be way, way slower. This is already not so bad. But let's see what Numb Expert can do with this. So in this case, I assume that I already have the A and B arrays and the C array there. I first want to just test the idea of it compiling. So I set the number of threads in Numb Express to 1. There's a function for that, set number threads. And then the way to evaluate an expression is to give it to the evaluate function. So I have A squared plus B squared. Notice how this has become a string. So it's a little bit funny, but that's what it is. It will figure out that A and B exist, what they are, pass them in. In this case, I want the output to go into C. I can also say C equals evaluate, I think, but this is one way to do it. And then I'm timing how long this takes. So Numb Expert now takes this expression, essentially compiles it, and then runs it with one thread. And that took 156 milliseconds, or sorry, 152 milliseconds. So kind of surprising perhaps how much of the system time got away, because I just said system time is something you can get away, but here system time is Python time, right? It's not operating system time. So Python time is interpreting this stuff again and again and again. And here, none of that has to happen because it gets compiled. So this speed up is not even using multiple cores. This is just using Numb Expert. This is the power of compilation. If I do set the number of threads to 4 in this case, and I do it again, this was running on my laptop, I got 208 milliseconds. So that wasn't very helpful here. But the wall time was much better. So So this is, you would see this in time too. So I have the user time, but it counts up all the time spent by all the cores. So I have 4 cores spending time, so I get more or less 4 times 57 milliseconds as the user time. So at this point, I have to stop using the user time as a measure of how fast things go, because it's, unless I divide it by 8, and I have to look at a thing that is called wall time. So different times now mean different things once we work in parallel. And so wall time is, in this case, something we're really concerned about. And that got about a 3 times speed up, which isn't bad, given that this didn't just evaluate this expression, but also compiled it and started it and stored things in these same arrays again. Okay? Yeah. No. So unfortunately, there is a limit to what Numb Expert can do. And if it doesn't fall within an expression that uses these things, then it can. So as powerful as it is in getting speed up, it's partly because it doesn't have to check a whole bunch of things when it's doing the compilation. The compilation is fairly straightforward because there's only so many options. That's why it doesn't hurt as much. You can do it within a function. Like this could be a line in a function, but then that line would now be evaluate this. Let's look at example for a second. So here's our Poisson function that I promised we would try and attack. And this is really not a bad function. It already uses NumPy. You can't see it from this, but P is a NumPy array, so that these function calls here, the exp, or npx, or NumPy exponent, actually takes the array P or negative P and then computes this in one chunk. This is tremendously helpful in terms of speed over doing this element by element. Don't iterate over a NumPy array or over a list. I mean, you can, but it'll be so much slower. Because at each time, Python has to interpret the line, check all of the types of variables. Here, all of that has been done once. So it's not bad, right? It's using a SciPy function here too. And because it's NumPy already, these are the kind of arrays that Numb Expert wants. So we're in good shape, right? We can really look at this carefully. So now the only thing that won't work very well with Numb Expert, so we have to change the code a little bit, is this factorial. But x is just a scalar function, so we just compute this once outside of the Numb Expert and then use it in the Numb Expert. So the change is really rewriting this to something that Numb Expert can use. So that's where I had to substitute the factorial, and then for Numb Expert also, npx should just be x. It knows that is what that is. It doesn't know what npx is. Okay. So I set the number of threads here to 4. That's just because my laptop likes 4. If you don't set it, it tends to use the number of cores that you have, which is usually the good thing. But if you had some other parallelism going on, maybe you ran 2 of these at the same time, you might want that fine-tuning at some point. So also, if you want to check your speed up, you might want to play with this just you're curious how fast would it have been if I had half the number of cores. So let's see how this does. So the serial case took about 18 seconds, and the Numb Expert one took about 11 seconds. So it's faster. It helps. You see that we didn't shave much off of the system time, as I said we wouldn't. But it's definitely not 4 times faster, although I'm doing 4 times as many cores. Why not, do you think? That could be an explanation. I think, and I think generally, there's a whole bunch of other code there too that takes some time. We didn't really check how much time of those plot commands was in the likelihood and how much was in plot. The plot part is still serial, so a good bit of the time must still be spent in serial. And we could investigate that further and see. But if it is in the plotting, we don't really have much control on how on parallelizing Python's plotting capabilities, unfortunately. Would be nice, but So I'm guessing a lot of this is just plotting and saving to file. Well, it knows about NumPy arrays, and it actually uses that because NumPy arrays are nice and contiguous in memory and have all kinds of nice properties that it uses. The exponent, and so the NumPy exponent is basically also using the fact that the NumPy arrays. But as far as Numb Expert is concerned, this is really just an expression that says take the exponent, and it knows what to do with that. And it'll do the equivalent thing of what NumPy would do, but it probably isn't calling NumPy for it. It has its own exponent function. Right. So that's nice, but also serves as a warning is that while this will help and it's great, your mileage will vary. Right? It just depends on how much of your code is parallelizable in this sort of an easy way, whether you get a speed up of this. Right? Now, we saw that it uses threads, so I have to mention that Python also has threads inside itself. There are native Python threads, which you would think, well, maybe I can get the rest of my code parallelized using that. Threads are a whole sort of model of how you program. You can spawn a new thread, you can have threads join, you can create new threads, etc. Which is all possible within Python, except, as it turns out, the most common implementation of Python, which is the one we all use, won't get any speed up out of it. It uses a thing called a global interpreter lock. So remember where I said that Python reads one line at a time? Well, even if you have multiple threads, it now has to read multiple parts of the code. And it won't do that at the same time. So essentially it means that although you can have multiple threads running at the same time, only one of them is active at any given time. And because of that, the amount of speed up you can get by doing threading inside Python with native threads rather than something that works in a library like Numb Expert, the amount of speed up you can get is virtually zero. The only good thing about using threads in that way is more for responsiveness. So imagine that you'd have some sort of graphical user interface that has to respond to mouse clicks and keyboard strokes and has to do a computation. By doing this sort of interleaving of things, rather than your mouse being stuck while it computes, you can still move your mouse, but the computation just goes a little slower. Okay. So it's good for responsiveness, but doesn't help for high performance computing. Okay, so that's one of the ways to use threads in Python in a way that actually gives you speed up. And it's an example of using shared memory programming. That means basically using threads on the same node. If you have to go across nodes, maybe your program is too big, your problem is too big to fit into the 16 gigabytes that each node has, you need 30 gigabytes, you need to at least spread it out over 2 nodes, then you have a problem in parallelizing that if you want to try and use threads, because the threads can't see each other from node to node. So the most common way to program these when you're not in Python is MPI. For a while now, MPI has been the standard of doing process communications for parallel processing. It stands for message passing interface. And the idea is kind of funny. Each process is its own thing, has its own memory, its own variables, and the other processes don't know anything about it at all. And if they have to know something about some of the other processes, they basically have to communicate. They have to send messages. So one process has to send a message saying, hey, here's my variable x, and it has this value. And then the other process, oh, I'm ready to receive a variable, and it just sits there waiting until it gets it. So you're very explicit in sending and receiving these messages, and data is one kind of message. So it's a little bit of a funny name, but that's what it is. There's the sending and the receiving of messages, but there's also the launching of these many processes that has to be somehow orchestrated. Because if you start a program on your own machine, it will not run on another machine just magically. So there's a protocol for that, and it goes through MPI run or MPI exec. It's a very explicit kind of interface. It has been ported to Python, which is actually kind of nice because a lot of the drudgery that you have to do in C or Fortran to get this to work, Python can do for you. So you get sends and receives, you get things like collective operations. You can imagine that these processes all have a number. Say it's a grid, and they each get a part of the grid to work on. They could compute, say, the total energy in the grid, and they compute their local energy, and then they reduce that. They sum that up. That's a collective. So there's some so different ways of sort of doing collective communications are there. Great. We'll talk about the optimized thing in a second. And it works very similar to C and Fortran, but simpler. So here's an example of a typical MPI process that you could run in Python. So MPI4Py is the module that you would use. And one of the things is that since these are completely isolated processes, what they will need to know is who they are. Because if they don't know who they are, they will all start doing the same thing. They will have to know which part of, say, the grid they're using by figuring out what their rank is in the array of processes. So there's a virtual array of processes, and they will ask, okay, what number am I? That's their rank. And they'll ask, well, what's the total number of us? So by that, they can figure out things like, okay, which guy is to the right of me? If I have, say, 10 of these guys, then number 10 will probably consider nobody to the right, or I could say, well, the guy to the right is, I just wrap around and I'll call number 1. So from rank, I can derive what to do. And in this case, what they do is something kind of silly. They send their rank to their left neighbor. So if you'd run that, they'd all say my right neighbor has a rank of this. So this is your code, and you'd run it through MPI run because you have to launch these things. So in this case, I launched 2 processes. The number of processes is 2. And each of them starts running this. They request, okay, what's my rank? And then they do something based on that rank. So coding this in and starting from only the rank that you have, and then making sure that you have your portion of the data, and you send the correct portions of the data to your neighbors that when they need it. That is a very intricate way, but basically the only way to do it, because you're not sharing memory between these processes. So it's possible and works. You can work with NumPy. I'll skip that because we're a little bit out of time. And I'll just skip to an example. So suppose that I want to integrate the area under this curve. It's the famous function 7/10 x cubed minus 2x squared plus 4. That, we all know why it's famous. And we want to know the area under the curve. There is an exact answer, so that kind of helped. And the idea is that you take many points along the curve, and you add up the function values, and you get an approximation. So you could do that in parallel by just segmenting up that array from that domain and program something like this. So it's a small code. It asks for its rank, and then figures out based on the rank where it should start. So x starts at a certain spot in the domain, and then it goes a certain part of the domain. And at the end, when it's done its own part, it communicates that to the rest by a reduction. So reduction in this case means the sum of all of these values, and then there's only one of these processes that is allowed to print, which is rank 0. The program says it's only that function that's allowed. Anyone could, but I don't want 8 copies of the same value. So just to show you how this works in terms of speed up, here's running it with 1 process. Takes about 300 seconds. Run it with 4. Takes about 56. So that's pretty good. So the nice thing about MPI is when you do it properly, it can scale very, very nicely. Like it tends to, the things that make programs not scale is typically either parts that are serial, so they're running and only one thing is doing something. In this case, they're all running all the time. So unless you do something very funny, it's very, like every process is doing some work. And there's no chance of sort of interdependencies that you don't really see. So for instance, you could imagine these, well, hey, memory access could be an issue, but that's it. There's two versions here, but they do basically the same things. So you can do either this threaded version where you basically use a library. You can do MPI4Pi. There's other possibilities. See if I can show that. Some of them are very popular. Spark, for instance, or PySpark is a Python version of Spark. It's very popular in sort of data science things, but they're really frameworks that are they can be helpful, but they all in the end either do threading or do inter-process communication. They might have ways to deal with parallel files or other things. That's fine, but the idea isn't any different. Okay. Questions? Yeah. I don't know if let me move them somewhere. Oh, wrong keyboard. Just put them somewhere. I don't think we have anything for this yet. So. Oh wait, I'm on tapping backwards here. Shall we call this? The 479? Okay. Yeah, not right. I know. Oh, that's okay. There we go. Six, 479, and then let me copy the code over there. Yeah. So, and that's. Okay, that's good. Oh. Yeah, that should be there now.